keep your eye in this region, and let me just re-execute this command, and perfect. So we have the foo.s. Now the foo.s, if you see, has all of this syntax, huge syntax. Something as simple as 3 lines of C code has yielded so many. But hey there. So in the video today, we're finally going to start doing something around the C language. And what I want to do today is, introduce the motivation for having the C language. So motivation for C language, right? And the second thing, so this is like the first thing. The second thing I want to do is, show you some demos, hands-on, and learn roughly 5 things about C language, right? We'll come to this part in a while, obviously. Let's first start off with this. So the question is, uh, why was even C language invented, right? Or well, it was not discovered, it was invented. Why did people work on it? Why did Dennis Ritchie and friends work on that? So let's go back to 1970s again and take a look at how the world was back then, right? So let's say you are a developer, you are a programmer, a computer engineer, you write some assembly code for a processor X, right? So you have this nice X processor, maybe IBM's some processor, or something like that. So you have a processor, and for that you wrote some assembly code. Remember, this assembly code would be written in the ISA of the X processor. That is how it was, right? That is how it is supposed to be. Now you take this file and throw it into an assembler, right? And this assembler is for the X processor. So this then generates the ELF, or let's just directly jump to the binary. So it generates the machine code, right? And for simplicity, let's say that this is the .bin file, and you have the zeros and ones here, right? Very nice. And then what happens is you load this on the system with your X processor, and the code happily runs. Everything is nice. And let's say to develop and test and debug all of this code, you took about 6 months. Now what happens is, let's say you want to share this piece of code with one of your colleagues in a different university, for example, and they happen to have a processor called Y, right? They have a processor called Y. Now what's the problem? The problem is that you wrote this program in X processor's assembly, or ISA, right? So your friend now has this entire your friend who is a professor in another university, he has an assembler for the Y processor, and then that would generate the binary file for the Y processor, right? But then the code, the thing is that you don't have this code, so you would need to, or your friend would need to spend another 6 months translating this code, this original piece of code that you shared, into the Y's assembly language, and that's painful. Now imagine what happens if the manufacturing of X processors stopped for whatever reason, and also for Y for whatever reason. Then this needs to be again rewritten for another processor, and that is extremely painful, time-consuming, painful. Then there is human errors involved. Testing takes time. All of that. So what people then did was they said, hey, let's have a higher level language, some language. I think there was B, A, B, and some other language, BPL or something. But let's say now you write the same code in C. The benefit now is you give this code to your friend who has, let's say, the compiler for the Y processor. He has the tool chain, so to speak, for Y processor. And that then converts your C code into the assembly language for the Y processor, which is then fed to the assembler, and then there's like linking and all of that, which is also here, which is also here, which I didn't talk about. But then, assembler linker, blah, 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 then there is a bin file. And that bin file can run on the Y processor, right? Very happily, it will run on the Y processor. And you yourself, who has the toolchain for the X processor, now have a compiler for X processor, right? And that will generate the .s file, which is fed to the assembler linker, whatever, right? And that also generates a binary, and that happily runs on your X processor, right? So the problem that C has ended up solving here is that the code need not change. People can reuse that code. So it essentially enabled portability across different processors, different machines. And that is very useful feature to have of a language. It saves pain. It avoids, it makes maintaining the code easier. But then not only that, the code is more English-like, as we shall see once we discuss the keywords and all of that. So it's more English-like, so more readable. And organization is better. Right? Code organization is better. We have portability, then by readability because it's English-like, and the code organization is better. So hopefully this convinces you as to why C as a language, got adopted. Or people even thought about it. What problems did it solve? Hopefully you're convinced about that. So that was pretty much, the first part. Now I should mention, as we learn the C language, we'll always go from C code to assembly code and stitch the generated assembly code. We'll stitch it back to our understanding of the assembly language that we already have, which is, the directives, labels, comments. So all of that. We'll go back and see what we wrote in C, how does it translate to assembly, and then automatically we'll know how it translated to the binary. This is important because this is where all of the insights of the C language are. Once you understand, why certain type of assembly is generated or what type of assembly it generates, you'll automatically understand why the C keywords are the way they are, right? So with this as our background, what we'll do now is go over to the demo part where we'll try out a few things on our own. So let's then, follow the usual song and dance, which is go to github.com/ inpyjama /c-ninja-listings, then find this button, which is the code button, then click on that. If you do not have a code space like I do here, the name can be different. If you do not happen to have that, click on this button here, the plus button, and a code space will be created for you. It might take about like 5 to 10 minutes, depends on internet connection and all of that. But if you already have one, then you should see this option, open in, then go ahead and open in the browser, right? And then we'll just wait for the code space to become active. It's okay, now it's loading. So what I'll do is put this in full screen so we have like all of the screen real estate for ourselves. Okay, so we will now just wait, and I will, randomly just draw a nice picture. And some hairs are awesome, ears. Yeah, cool. Okay, yeah. So once the environment is loaded, you should see all of this. Now what we want to do is write some C code and then see the assembly that it generates, and we'll also try to run execute on QEMU the C code. Okay, so now the question is, how should we learn C language? So I thought about it, and one way to do is, learn the keywords, then, learn data types, then the usual, if condition, for loop, whatnot, blah, 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 all of that. That I feel is a very flawed way of learning any language. One should start with the motivation as to what problem the language is solving, what keywords it provides, and how to use those keywords, right? So in our case, we'll start with the concepts of function, right? We'll start off C language straight from the idea of functions, which is essentially uh, grouping, expressions together, right? What an expression is, we'll take a look at that as well. But this is the path that we'll follow. So we'll, go down the functions route. Okay, so now what we'll do is we'll take our previous example that we have been exploring for this long, which is the test directory. We'll simply copy that and simply paste it, right? So to copy it, simply right click and copy, and then just click anywhere here and hit paste. And once you do that, a test space copy will be created. What we'll do is we'll go ahead and rename it to C-ASM, just because I want to emphasize on the relation of C and assembly as part of this video. Okay, so what we have now is the same old main.s, the good old make file, and the linker script. So the explanation to all of this is already kind of given in the previous videos. And to be able to follow this video, please make sure that you have an understanding of the prior videos or the concept shared there. Nice. So what we are now going to do is create some file. So foo.c. So C files, C source code, they have an extension of .c, right? And if there are header files, which again we'll take a look at later, so they have the extension .h, right? So .c and .h are the usual extensions, right? So we have created a foo.c file. Now, if you have any familiarity with C, you would kind of, have heard of the main function, right? So people say that, main is the entry function in C. So that is incorrect. Okay. So usual C code does have the main function. That is correct. But it's not a mandatory thing. For program written on operating systems, yes, main is the entry function. Main must exist and the code starts off from main. But in our case, given that we are going towards embedded systems development, this is not a necessary condition, right? So what then we are going to do, so let me just maybe, increase the font size here. Yeah. So what I'm going to do is first write some command or some, statements, and then explain those. Um, and that's about it. So let me just zoom this, out of proportion, just so that we can talk about things. So remember I mentioned that we will learn 5 things about the C language. So let's start. So this is a C function. So this is a function, right? And this is the name of that function. Okay, so bar is the name of that function. A name can be anything that the user wants. The rules are it should start with alpha, it should start with an alphabet, okay, let's see. So this is the function, this is the name. The constraints on the name are, it can be anything from A to Z, caps or lowercase, and followed by underscore. And then there can be more, A to Z and capital A to Z. There can be numbers also in between. That is also allowed. It's just that it should start with an underscore or alphabets, right? Right. And no special characters apart from underscore are allowed. Again, we'll take a look at the details of the naming convention when we deep dive. But for now, know that there is like no restriction on what uh, this name can be if you know comply by these rules. Also, this is completely up to the programmer, right? These parentheses here are mandatory. You know, there can be things that go between these parentheses. Those are called parameters. Right? In this case, there is nothing, which means there are no parameters. And what parameters are, we'll also come to that in future videos. So the idea then is that this is the only thing that is non-C, that is like the programmer has the freedom of it, writing it. Void is a C keyword and return is a C keyword. So let me just write down here. So in terms of keywords, there are two, void and return. All keywords are lowercase. Like for example, in Python, the true and false and none, they start with uppercase. But in C, nothing starts with, no keyword starts with an uppercase. It's all lowercase. So let me write our notes here again. So keywords wise, we have learned void and return, right? So the idea of a function is that a function is a group of statements. It's a group of expressions. And uh, so the function can essentially compute something and give back an answer. Again, what give back an answer means will be clear once we dwell more into the C language. But then the idea is that the void keyword suggests that it returns nothing, right? And if you see the return statement here, um, well, usually return can be followed with something else, and there is nothing here in this case. In this particular case, there's only a semicolon, so it means there is nothing being handed back. So this function essentially in this case does nothing, right? But return is a keyword, void is a keyword. Void is we call it a data type. So in this case it's like a return type, and let me not confuse you more. This curly brace and this curly brace are important. So anything that goes between the curly brace belongs to the function here, right? So this is us saying, hey, we are kind of now starting the grouping of the statements. And this is like, okay, we are stopping the grouping of the statements, and all the statements between these two curly braces belong to bar function, right? That is the idea. So that was, the second and the third thing, which is this is for parameters, right? And the third thing was between curly braces, we say it's a code block, right? A block of code or a group of statements. The fourth thing that we want to take a look at is this semicolon here. So every expression ends with a semicolon. Every statement ends with a semicolon. And this is the delimiter. Okay, I think I got this wrong. Something like this. So this is the delimiter. It ends the statement in C. What was the fifth thing? Okay. Now this function here, C kind of treats all white spaces as single space. So if we had written something like so, okay, curly brace, space. So there's a space here. There need not be space here, but there is a space. There should be a space here. And then if we say return, this is a valid C code, right? So after every keyword, there should be space and or a delimiter, right? So that's the idea. So we only learn these five things, spaces, white spaces essentially. treated as a single space. And keep working. Yes. Okay. So those are the 5 things I wanted you to note about the C code. Now, what we are going to do is try and generate assembly out of this. So first off, let's actually get rid of all of this. So how do we go about generating the assembly? So we are going to go to our make file, right? And let me just zoom out a little bit. So we had all of this code. What I'm going to do is add a target called ASM, and then hit tab. And again, the makefile related syntax and how makefile needs to be written, we've discussed it in earlier videos. So what I'm going to now do is copy this line here and modify that a little bit. So here again, we have this GCC compiler, which is right here. To that, we are saying, okay, all of this, machine related stuff, blah, blah, blah. Instead of this now, I'm going to give it foo.c. Then I'm going to give it foo.c as a dependency here. And I'm going to change this a little bit. So I'm going to give it the -s option. And what that does is that essentially says, hey, take this foo.c file. Let me just draw something here. So take the foo.c file and then convert it to foo.s file, right? And preserve this, show it to the user. That's the idea, and just stop there. So in all of this, compiler flow that we talked about, it'll just stop at this point. That's the idea. Okay, so let's go back then. And yeah, so we want to, this option essentially is just instructing it to go from C to S. Let's see, hopefully I got the syntax correct. I save it, open a terminal by, let me pull myself up here so that you can see the keystrokes. So control tilde and I get my terminal. Then in the terminal, what I'll do is I'll go to the C-ASM directory and then do make ASM, right? So I am at this point invoking make, asking it to call the recipe associated with the ASM target. And as a result of that, it should have executed this one line, which is exactly here. Now we should also see that it has generated the foo.s here, right? And to just show you this again, let me go ahead and delete foo.s. Keep your eye in this region and let me just re-execute this command. And perfect. So we have the foo.s. Now the foo.s, if you see, has all of this syntax, huge syntax. Something as simple as 3 lines of C code has yielded so many. But there is something interesting to note here, right? Which is, if you see, so there is this bar as a label, right? And then here is like the description of what bar is. Bar is a global label or a symbol, and then it is of the type function, right? Which means the assembly code can jump to this label, right? That's what it means. Let's not discuss all of this. This is not super important, or it would not add to our understanding of the C language just yet. And then if we go towards the, okay, all of this is also, completely useless. The part that is useful to us is this line. Right? So JR is an assembly instruction which says jump by using the address in a register, and the address in the register that it needs to use is the RA register. So this, my claim is equivalent to the return statement. So this is where the function starts. This is the body of that function, which effectively does nothing. All of this is just because we have zero optimization. So leave all of this at this point. And this last JRRA corresponds to the return. So what we now know is that a function name will translate to a label. BLE. Yeah, it will translate to a label. Actually, I can't spell, so label, I might have spelled it wrong also. Right, so let me get rid of that. So yeah, this is the label and this is the written statement. That's the point. Okay, now what we want to do is we somehow want to execute this code in the sense that we would want to, jump somewhere here. We would want to see this executing. Okay, so now for that to happen, we will need to modify our makefile a little more, right? And what I'm going to now do is close the foo file. Let's do this. Let's, take this all target and add the foo.c here, and then just throw in the foo.c in this place. What will then happen is both of these will be submitted to the compiler, and the compiler will kind of go through linking phase, this, that, assembler, blah, 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 and generate the main.elf, out of which we'll get the main.bin. And that main.bin we can run. Okay, so let me just go ahead and make those changes then. Foo.c, I add foo.c, save this, then again, go here to make clean. And remember, I also have to delete the foo.s, right? Okay, and then I'll just do make all. If, yeah, okay, we also have too many prints here, which is nice. But look at what happened here, right? So when we called the, okay, actually, let me also scroll up, right? So if you see the main.sn foo.c, those are available here. Then main.bin, compared to the previous time, this has like a lot many instructions. The interesting thing is this instruction here is the same as what we have here, right? So in the previous videos, we have seen this, and rest all instructions are corresponding to the foo.c's bar function, right? Okay. So now there is going to be a problem, but let's discover that problem together. So much like the previous, time, what we'll do is we'll come here and, okay. Okay, so what we are going to do is make debug to start our QMU with the main.elf loaded in it. Then I'll create another, terminal, and what we'll do is we'll do make GDB in it, right? Okay, I need to go to CASM and then do make GDB, right? So once we do make GDB there, as expected, actually I should reduce, right, zoom level. So once we are here, we see that we are at this point, right? And now from the problem is where is our code? And then just based on the prints here, our code starts from this address. Now, if I were to do an NI, right, you see that all of a sudden the C related code appears and the program counter is pointing to bar plus 4 something something. Right? So this is a good hint that our C code is somewhere involved. Now the interesting bit is if we go ahead and do NI, we'll be executing code that is part of the bar function, right? And there is a big problem here that we have not run into just because pure luck, and that has to do with the fact that that has to, okay, let me just give me a moment. Let me fix few things. So I would want interactive mode. Yes. Press and hold. Okay, I shall do that. So, this is interesting. Give me a moment. Right. Okay. Very nice. And we have technical problem here. Okay. How do I get rid of this arrow? Oh, maybe, yeah, okay. Right. Nice. So Okay, let's see. Right. So I was mentioning that we purely got lucky because the bar related, code was put right under the start label. And so our execution just fell through. So this point here happens to be, right below. But that would not always be the case depending on how the linker script is written. So one of the ways in which we should fix this, and we'll kind of take a detailed look at all of this in later videos again. Okay, why cannot I quit? Hello, yes, okay. So let me quit this and let me also get rid of the 𝗁𝗵𝗶𝗀. The way to go about in the right sense calling the bar function is that we say jump and link and then call the bar label, right? Remember in the foo.s, a bar was a label, and that's what we are saying. This is also, by the way, how we call C code from an assembly code. We just refer to the function as the label and jump to that label, right? So this is the jump instruction, right? Okay, I think I don't know, I don't remember if JL is the right assembly instruction, but I know J is. Let's try both JL and J and see. Jump and link, I think, is an instruction. Okay, so we do make all again and something happened, so it doesn't recognize JL. So let's just go ahead and use J. J is for jump, and let's do make. Yep, everything just works. By the way, it has just created the foo.s, which we don't want, so let's delete that. Let me do make all. Right, so make all went through, everything is great here. Now what we'll do is we'll do make debug and then do make GDB here, GDB. Right, so now we have the jump instruction here, and that jump instruction properly sets the program counter value to the bar function's address or bar label's address. Well, the bar label itself denotes or represents an address, so program counter will point to that. So if I do an NI, we see that program counter points to 8 all zeros 4. Now I might have created some confusion, and it might be not very obvious as to why go about doing a J when we were following through correctly. To explain you why it matters, let's do this. And the territory that we are entering now, we would require a little more of assembly hack to make it work, and that we'll do in the next video, but I will show you something. So let's say we have another function now, and you can have a number of functions in the same file. Right, so this happens to be one function, this happens to be one function, returns nothing, returns nothing, and void represents that nothingness, right? Same story with the foo. So I'll also have like a return here. Also to prove the point that spaces are not, the white spaces are not necessary, I will write it this way. Okay, now note that if I go back to our previous code, our intention is to jump to bar first, right? And now if I were to do make all, make debug, and then do like a make GDB here, and then do an NI, note that we have landed in the foo function, right? We wanted to go to bar, but we landed in foo. This is where we are, right? And the interesting thing then would be that if we go on, at some point it just runs into an error, right? Why that error? We'll come to that in next video. But let me now go back and show you how to fix calling the bar function, which is j bar, right? If we do this and repeat all of the previous steps, which is make debug. Oh, sorry. We should have first done make all, right? And then we do make debug, and then do make GDB. Now if I do an NI, it should jump to the bar function, right? And if you see, it has actually jumped to the bar function because this is in bright green. And if I scroll up, you see, you should see the assembly that is highlighted for the bar function. Now, this one line here is these three assembly instructions. That's why, all of these are in green. Well, with this then, hopefully I've convinced you about why C as a language was needed, what kind of problems it solves, the portability issue, the fact that we will always go back to assembly code from C code and understand the C keywords, and then finally how we go about stitching the assembly with C. And I just want to comment again on the last part, which is why is stitching assembly and C so important? Remember that when a processor boots up, it'll just start off from some memory location, and usually there is some assembly required to set up some sort of preconditions for C. And just because we did not have all those preconditions in place, we saw an error when we were trying to just do an NI with the foo function, the fall through. So hopefully this video was useful to you, gave you an insight into what C language is and what's the background. And I will catch you up in the next one where we'll dig more into the C language. Thank you for sticking around. Catch you later. Bye-bye.